Hello, this is Jesse Pisors. I am happy to be here presenting for the Introduction to Educational Statistics class, EPSY 5380 at Texas Tech University. I'm going to talk a little bit about correlation and specifically a few terms within the concept of correlation that I think are important, obviously, within the introductory level of statistics. This is a very important concept and one that we've certainly looked at in this course. So to begin with, just a moment of levity, perhaps a cartoon that you've seen, the erroneous assumption that if the number of shaved heads increases, then the amount of sales might also increase. That would be a serious and tragic misuse of the concept of correlation, which we'll discuss in a couple of minutes. So correlation is a statistical procedure that can demonstrate if two variables are related, and if so, how strongly. Correlation embodies the concept of relation or relationship. And I think in this explanation, I'm going to try to use my own words and explain things in a way that makes sense to me and hopefully might make sense to somebody else in the same way. But there are two variables and a correlation techniques, and there are several different correlation techniques show how those variables are related, if they're related, and how strongly that relationship is. The first correlation that we'll look at, and probably the most common and the most important, the most widely used correlation statistic to determine the degree of a relationship between two linearly related variables. So if you have two continuous variables, and that's very important, the Pearson correlation can show the relationship between them as long as those variables are linear. So for example, if you have the number of hours that a student studies in a semester, which could be counted linearly, 1, 2, 3, 4, 5, up to 100 hours, and then you might have that correlated to the grade that they got, a 60, a 70, an 80, a 90, a 94. That also is a linear continuous variable measurement. The Pearson correlation would be used to determine the degree to which those two continuous variables are related linearly. Again, this is the most common correlation technique that is looked at. In the Pearson correlation, you have positive, negative, or no correlation, and these graphs illustrate fairly well how that is. In the positive correlation chart, you can see that the values on the x-axis move over to the right and get larger at the same pace that the y-axis values also get larger. That's a positive correlation. Then you have a negative correlation where actually as the y-axis values get higher, the x-axis values get lower. And then no correlation, the way I see this is you've got dots all over the place. So there is no correlation, and that just illustrates that fairly simply. The Kendall correlation is a more advanced correlation technique to use when measures in sets of rankings are not equidistant, non-parametric data. So to go back to the example I talked about earlier, when you're looking at the number of hours per semester that a student studies and trying to find a correlation to the grade that they got, that every 1 hour would be separated by one number. Every grade might be separated by 1 percentage point, a 92, a 93, a 94. That's when a Pearson correlation is used. But if the distance between the rankings are not the same, they're not equidistant, 1 unit apart, it's non-parametric data, and that's when you might use a Kendall correlation. Again, that's a more advanced technique that we didn't use in this course, but if we're looking at correlation, it's good to at least mention it. The Spearman correlation is kind of like the Pearson correlation plus. So it's an advanced version of the Pearson correlation, if you will, because it measures not only the fact that there is a relationship and the direction of the relationship, but it measures the strength of the relationship as well. So you can not only see, for example, that there is a correlation between the number of hours that a student studies in a semester and the grade that they get in the course, but you can see how strongly that connection is. For example, that for every 10 hours of study, you can see that their grade goes up by 1 percentage point or something like that. So that would be when the Spearman correlation would be used. It's very important to remember in correlation that we're talking about quantifiable variables or continuous variables such as numbers, not categorical variables such as gender. And of course, in these courses and in the videos, our professor talked a lot about the difference between continuous variables and categorical variables. So we remember that if you can't use a Pearson correlation, for example, to try to correlate the male and female to grades. You of course could do statistical comparisons, but you wouldn't use exactly a Pearson correlation to make that. You could look at the mean or the median or the mode grade that different genders got on different tests, but when you're doing pure correlation, you're looking at quantifiable numbers, not categorical variables. Within the concept of correlation, you have a very important term, which is the coefficient, the correlation coefficient. The main outcome of a correlation is the coefficient, and that coefficient is represented by the letter r, this lowercase r. The range of the value of r could be +1 to -1. So most times when you're looking at the r value of a correlation coefficient, you're looking at something like point something or negative point something. The closer r is to +1 or -1, plus 1.0 or minus 1.0, the more closely related the variables are. So that's important to remember. A little bit more about the coefficient. Now, if r is 0, this means there's no relationship between the variables. If r is positive, that means that as one variable gets larger, the other variable also gets larger. If r is negative, this means that one variable gets larger, the other gets smaller. So going back to our example, you might find a positive r coefficient by saying, yes, we notice that the greater the number of hours that a student studies in a semester, the greater the higher the grade. So that might be a positive correlation coefficient, a positive value of r. Now, an inverse correlation is also what is referred to as whenever you see r as a negative number. This means that as one variable gets larger, the other gets smaller. So you might say, well, let's try to look for a Pearson correlation on the number of hours playing video games and the final grade that a student gets in a course. So as the number of hours playing video games goes up, the grade in the course goes down. That would be a negative r, and that would be an inverse correlation. There are limitations to correlation. It's very important to remember this. Correlation does not tell us everything about the data. Mean and standard deviation continue to be important. Complicated data may be better described by a curve than by a straight line, but a curve will not be revealed in the value of r. So I think in the wide world outside of statistics, a lot of people think a lot about the term of correlation. It's used a lot in our common vocabulary, but really there's a lot to statistics that help us explain data that is outside of correlation. It's important to remember how much outliers influence the correlation coefficient. Going back to the example, if you, for example, find that for every 10 hours of study, a average course grade improves by 1 percentage point, but then you suddenly see that for one student they actually only study 1 hour and they get a 99 in the course. That would probably be an outlier and it would influence the coefficient. You'd have to decide what to do about that in order to get a good information that would be valuable. Probably the most important thing I can say about correlation, and something that's been said a lot and you hear a lot, is that correlation does not necessarily mean that one variable causes another variable. but it's simply correlation does not imply causation. We go back to the cartoon I showed at the beginning of the video, that the more shaved heads there were in the company, the more sales went up. So the boss said everybody needs to shave their head, so we'll get more sales. Well, that's the erroneous conclusion that correlation implies causation, and that's not the case. Now, it may be true that the more hours you spend studying, the higher your grade will be, and you have in fact caused one to go up. But the simple act of doing the correlation and applying that statistical technique does not in and of itself tell you that there is a causation there. So the causation may exist, but correlation does not necessarily imply that causation exists. And we'll end with this cartoon that I think illustrates this. We may have thought this before the class, then we took a class and it doesn't. So does that mean that the class made us not think that? Well, maybe, but the simple principle of correlation doesn't tell us that. We have to look a little bit deeper. So I hope that tells you a little bit more about the concept of correlation, a very important one to statistics. Thank you.